So today's lecture is more of the discussion that we've been having last time about operating systems and the necessary hardware support that they need to implement the features, the functionality that we expect now from modern operating systems that don't suck. We'll also start to talk about operating system architectures today, which is a really interesting discussion that will spill into Monday's discussion, where I think the really exciting and interesting stuff is that we'll discuss. But to set up for Monday's discussion, we obviously need to talk about a certain number of things. So let me see if I can get the slide to move forward. So we talked about these components last time. Remember that we have the part that is the operating system proper, and that tends to be the stuff that lives in protected mode. So we're talking about the kernel itself, and the way that applications interact with the kernel is through system calls. But there's also portions of the operating system that live outside of the kernel, the command shell being a notable example of that. Your graphical user interface desktop, those kinds of components are also notable examples. They don't run in kernel mode, but they depend heavily on system calls, of course. So lots of interesting details. We talked a lot about that last time. Let me see. Applications can't access the OS state or code directly because that would be bad. And let's see. Yeah, so you have this ability through the virtual memory system to say this part of the address space is only accessible from kernel mode. This part of the address space is only accessible from user mode. And so we call them kernel space and user space for obvious reasons. So the first question we're going to talk about is how does the application actually interact with the operating system? And the way that it works on x86 is through this mechanism called a trap. And you see traps in virtually all operating systems, all processors that support reasonably sophisticated operating systems. It's basically a special instruction that allows you to transition from user mode into kernel mode in a controlled manner so that the operating system can govern precisely that transition from user mode into kernel mode. Okay. And I have a few other things listed here. Faults. We'll talk a little bit about faults in a sec, but if your program does a divide by zero or it accesses an invalid address, like what happens when you dereference null in your C or C++ program, it generates a fault because your program didn't know it was going to fail. The processor didn't know it was going to fail. And the way that that is signaled to the operating system by the processor is through the generation of a fault. So traps are intentional. We intend to go into the kernel. And so the OS, when it's booting up, is going to initialize a handler that handles all the traps. And it tends to be on a specific interrupt. I should probably talk about that in a second. But different processors may have different mechanisms. And in fact, x86-64 changes the mechanism from what IA32 does. I'll mention that in a second. So a benefit, think about this as a level of indirection. If I can just invoke a trap instruction and somehow tell the operating system, this is what I want to have done, then I have insulated my application from OS changes and OS updates. Because invariably, when you change the functionality of an operating system, you install the next point release of the OS or whatever, these specific addresses of operations will change inside the kernel. But since I am entering into the kernel through this generic mechanism, typically signaling the operation I want to perform by a specific register value, something like that, the application doesn't have to know anything about how the OS actually provides that functionality. And so anytime you have a level of indirection between components that are loosely coupled, it allows you to upgrade one without affecting the other one adversely. So that's a very powerful mechanism. You see it all the time. And then the other part of this, which is really good, is that the OS doesn't have to automatically do the things that the application requests, because the application may be broken or it may be malicious. And so the OS can say, sorry, that's a bad request. we'll talk about some of the things that can be done in subsequent lectures, because when we start really bulletproofing the operating system, it's got to be able to look at the request and decide if it's a safe thing to do or not. And that is a central part of how modern operating systems protect themselves from rogue applications. Okay, IA32 has a specific instruction called int, which just means interrupt, and it's used for triggering software interrupts. And so typically the operating system will set up a specific interrupt number that is the trap handler for the operating system. So Linux up to, all 32-bit versions would have int 80 hex would be the interrupt through which applications could talk to the kernel. There's a bunch of others. I think Windows is interrupt 2E, although now there's other ways of doing this, so we don't really use int instructions anymore. You will in Pintos, because that's how Pintos does its magic. So IA32 different operating modes have different stacks, and so this is important because a user application may have used up most of its stack space, and you do not want a system call to be sensitive to the way that the user application is behaving. So the processor switches to a different stack when it's changing protection level. So the kernel can have its own separate stack that is not affected at all or can be affected at all by the application. And because you have these different stacks, the arguments are passed in registers instead of on the stack. So some of you may be familiar with how calling conventions in programs worked, and in the past, especially in 32-bit, arguments would be passed on the stack. Now we have enough registers on x86 that we pass a lot of things in registers instead, but that's a little bit of an aside. There's some information about this in the Pintos documentation. So this is a simple example of how you would get the process ID of a process on 32-bit Linux. And it also would work on Mac OS until 64-bit became the norm. So you put a specific value in EAX. This is how you say, this is the system call I want to perform. You trap into the kernel. You say int 80 hex, and the kernel has a trap handler registered for that interrupt. And it says, hey, they want to get the process ID of the calling process. So they pull it out of the kernel data structures, plop it into EAX, and then iret back to the calling process, and the process now has its process ID. It's simple as that, really. Now, we don't want programs to have to do this for a couple of reasons, actually. So there are all of these wrappers around system calls available. So you don't do trap to invoke read or write or dupe2 or any of these kinds of operations. Instead, you call the C wrapper function, and it takes care of getting into the kernel for you. And part of the reason why this is great is because it turns out that int is kind of slow. And around Pentium 4 processor, that around that version of the processor, people started discovering, wow, trapping into the kernel in this way is really slow. And so a couple of new instructions were introduced. There's sysenter and sysleave, so that's a pair to get into the kernel and get back out. And then also syscall and sysret. So modern operating systems on x86 won't use int anymore to trap into the kernel. They only use syscall, sysret, or sysenter, sysleave. So, but on Pintos, we'll still use int to get into the kernel. The way that this mechanism works is it's driven by a table that the operating system sets up at boot time. There's this thing called the Interrupt Descriptor Table, which has these 8-byte entries, and each entry corresponds to a specific interrupt number. So you set up this table, and you put all your little entries in there, and then when the user application says int 80 or int 30 or whatever it says, the CPU actually looks up in the interrupt descriptor table what handler is this interrupt is for this interrupt, so that we can go ahead and handle it. So so protected mode has these 8-byte interrupt descriptors, which basically it's a simple set of rules. Caller protection level, the handler protection level and the address of the handler. There's not a lot more than that in the interrupt descriptor table entries. And so for an OS entry point, you would say, starting in at least user mode, you end up in kernel mode, and here's where the handler is located. Okay, and that way the kernel can control exactly how the program gets into the kernel, and it can be really careful with that code to keep anything horrible from happening. Okay, so a program issues an N instruction. This is easy to figure out, right? N shift left 3 bits. Well, that multiplies it by 8, and now we can use that as an address or an offset into the interrupt descriptor table. The base of the interrupt descriptor table is in a special control register on the processor, and off you go. Okay, the processor does all of its magic to get into, let's see. So if the caller has at least the required privilege level, the processor transfers control to the handler. Handler runs at the privilege level it requires. Okay, it's not that exciting, but it's certainly cool what you can do with it. Now, when the interrupt handler finishes, it issues an iret, and that basically undoes all of the steps of getting into the kernel so that you end up back in the user mode program. Probably the most interesting part of this is that you end up back in user mode. So simply by returning from the kernel using iret, the iret instruction, you end up back in user mode. So this is how the kernel can just take care of something, iret back, and you end up back in user mode, back in your restricted level of access. Okay. LIDT, that's the instruction you use to set the start of the interrupt descriptor table. Fortunately, you don't have to do this yourself, but I want you to see the information so that if you go snoop around in the Pintos source code, which I certainly hope you will do, you can see where this instruction is invoked to set up the interrupt descriptor table. Fortunately, all of this is handled for you, but it's great that it's there if you want to look at how it works. Okay, yeah, and then this is just a little bit of peripheral information. When you boot up a processor, an x86 processor, we'll talk about this a lot more next week, but when you boot up the processor, it starts out in ring 0, which makes sense because the first thing that runs is the bootloader, and then the thing after that is the OS kernel, and the kernel's got to configure all this stuff. How would it get into ring 0 if you didn't already start out there? And so it sets everything up. And once everything's initialized, then it switches into the appropriate protection level for normal operation. So we'll talk about that in a lot more detail next week. If anybody has any questions, feel free to plop them in the chat or just blurt them out. We're going to take a little bit of a step back and talk about exceptional control flow, because the int mechanism on x86 and traps in general are a part of this exceptional control flow mechanism that you see on processors since like the 60s, the 50s and the 60s. So exceptional control flow, the way that this works is you either have an instruction that intentionally generates an exception, or it accidentally generates an exception, or a piece of hardware may generate an exception as well. Okay, so we saw traps. These are intentional. And you'll notice here, I say that where you come back to, you return to the next instruction. That, again, should just make sense because it's like calling a procedure, except that the procedure is in a different protection level and it's inside the kernel. Okay, then you have interrupts, which are generated by hardware. So the disk controller says, hey, the data that was requested just showed up. So then a hardware interrupt is triggered by the disk controller. Or you type keys on the keyboard, hardware interrupts trigger. A timer goes off, you get a hardware interrupt. And these hardware interrupts are never dispatched in the middle of an instruction's execution. An instruction will end, any hardware interrupts are dispatched, and then once those interrupts are handled, then you go on to the next instruction. Okay, so that's why it says here on the slide, it returns to the next instruction. Okay, this is a bit of a misnomer. The current operation is interrupted. That's at a higher level of abstraction, but individual instructions are never interrupted in the middle of the instruction. It's always after the instruction's finished, then hardware interrupts are serviced, and then the next instruction executes. Okay, faults. Faults are interesting. They'll be your life in a few projects. They tend to be unintentional, and it's simply the execution of an instruction. There's a failure, but it is potentially recoverable. That's the key phrase here, potentially recoverable. So you have a page fault because a page of memory isn't in physical memory, then you would generate a fault. And then if the OS can resolve it, then it will. And when you return from the fault handler, you end up going back to the same instruction that triggered the fault, because now it may be possible to execute that instruction successfully. So if the OS ever has a situation where the fault is not recoverable, it's on the OS to say, sorry, process, you tried to do something, I couldn't figure out what you mean, and so I have to terminate the process. This is what happens when you dereference null in your programs. The OS kernel gets a fault, and it looks at your address space and says, oh, there's nothing at address 0 in your program, therefore the process needs to be terminated. So that's a great example of where potentially recoverable scenario is not recoverable. Then the last one you can have happen is an abort, which is a non-recoverable hardware error. So you get a parity error because you're not giving your memory enough power, something like that. If you have a computer that you can control the voltage levels to your memory or the clock speeds to your memory, it's pretty easy to end up with parity errors. And that would be an example of an abort that occurs that tells your computer just says, I can't continue. We need to just stop. Now, so machine check. I want to mention a specific kind of abort that you will probably see. In fact, when I was setting up the virtual machine and setting up the code base for this term, I ran into this specific abort, and it just was like, oh, not again. So it's always exciting when this happens. So IA32 has this thing called a double fault. Because what can happen is you can have a program running and you get an interrupt. Okay, no biggie. You go try to resolve the interrupt. So you look up in the interrupt descriptor table what handler to invoke. All reasonable so far. The problem is that during this process of interrupt dispatch, another fault occurs. Okay? And it could be a number of different kinds of faults. Well, what do you do if you have a fault while you're servicing a fault? Well, that's where the double fault handler comes into the picture. Okay, so the operating system can register a double fault handler. If you have a double fault, it is virtually always because there's a bug in the operating system. Okay, so this is an important key. If you see a double fault, it's because there's an OS bug. Now, here's another one. You have a program that generates a page fault because it tries to access memory that's not currently mapped in its address space. And the CPU tries to invoke the page fault handler, and then that generates a fault during the interrupt dispatch. Okay, so like it says here, it causes another page fault to occur. So that would be a double fault. Okay, this is interesting. Possibly useful information to know. Let's continue chasing this down. So you have double fault occurs, and then the the CPU tries to dispatch the double fault to the double fault handler, and a failure occurs during that. Well, if that happens, you end up in triple fault land. Triple faults are basically when the CPU says, that's it, I've had it, I'm rebooting. Okay, so that's a situation that you can get into. And so what happens is the CPU will basically trigger a reset and start over from the beginning. Okay, now you will almost certainly see double faults and triple faults during the term. Like I said, I saw one when I was setting up the project code. Okay, so you will run into this, and the way that it manifests is you see the virtual machine, not the virtual machine that I give you, but QEMU or Box, the emulator that you'll run Pintos in. You see Pintos reboot, 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 reboot over and over again. Almost certainly that's because you're seeing fault, 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 you know, first fault, second fault during the first fault dispatch, third fault during the second fault dispatch, and you end up with a triple fault and a reboot, okay? So I just want you to be aware of this because almost certainly you will encounter this, hopefully not until you get into system calls or virtual memory implementation. If you see it earlier than that, then we will certainly be there to help you through it because it's confusing the first time. I mean, there's new ways for your program to infinite loop now when you're implementing an operating system. Okay, so now you know. Now there are, how shall I say this? There's another hardware facility that's really important for modern operating systems, and it relies heavily on this hardware interrupt mechanism, because you can have programs that cooperate as far as sharing the processor. We call it cooperative multitasking, where basically programs will voluntarily relinquish the processor when they're done using it. And this happens in a number of ways. A program can yield. A program can make a long-running call. It can access data on the disk. It can ask for user input that implicitly will yield the processor. Or it can terminate. That's an obvious one, right? It's giving up the CPU. So these are examples of cooperative multitasking. The problem is that when a program on such a system doesn't cooperate, either maliciously or because of a bug, so let's say it's stuck in an infinite loop, then it never relinquishes the CPU, and that makes everything else stop, because everything else gets to run when the current program says, I'm done using the CPU. So for a long time, PC-based operating systems only provided cooperative multitasking. So Mac OS up to Mac OS 9 only had cooperative multitasking. Windows up to, but not including Windows 95, only had cooperative multitasking. Okay? This is problematic. You could have a device driver with a bug in it, and it would cause your entire computer to hang. And this is no fun. So the way that we solve this problem is through a hardware timer. You have a hardware timer that's only configurable from kernel mode, and you set that sucker up to go off at a certain time and preemptively force the current program off of the CPU. So as you would imagine, let me see, this is called preemptive multitasking. And we want preemption because we can build much more robust operating systems. Programs don't have to think about whether or not they need to yield. They can just do their thing, and the OS will take care of kicking them off the processor when it's time. Okay, so preemptive multitasking is a really important OS feature for modern operating systems. Like I said on the previous slide, UNIX has had this forever, but it's more novel, let's say. Now, I mean, we're talking mid-90s novel, but it's still pretty novel when it comes to the overall lifetime of the x86 processor family. Okay, so yeah, this requires kernel mode access. Otherwise, a process could just turn off the hardware timer, and it's now escaped the constraint that the OS is trying to impose. So the stuff for configuring this tends to be at a protection level that user applications can't deal with. Okay. All right. So that's pretty important. I'm going to skip over these slides. Maybe I'll just show you a few little details. Current x86 processors have this thing called the Advanced Programmable Interrupt Controller. And this is the thing that the OS kernel talks to configure these kinds of things. Pintos, being an older school operating system implementation, uses the predecessor of this thing called the PIC, the Programmable Interrupt Controller. So you can see APIC is just the next generation version of the PIC. So let me see. You have two components. You have the local APIC, which is basically devices, I/O devices that are connected directly to a processor. Timer interrupts are generated from the local APIC, and then a few other things as well. Okay, but I'm not going to spend very much time talking about this. There's also an I/O APIC, and this is particularly important when you have multi-core or multi-processor systems, because the I/O APIC allows multiple processors to interact with each other. Let me go ahead and jump up to this picture right here. So these things are connected via a bus, and when you have a multi-core system, one processor may need to talk to other processors, because let's say that you have a program that's got 4 threads, and the program needs to be terminated because one thread misbehaved and the other processors are running other threads from the same program. Well, the way that the OS tells the other processors stop running this program is by sending what's called an interprocessor interrupt. I have a little bit of detail about that. Fortunately, we don't have to think about this. Pintos is a single core operating system. I would love at some point to teach a class where we talk about multi-core operating systems, because there's a lot of interesting nuances. The OS basically has to think about what the other processors are doing, and it has to signal sometimes that important things need to happen through interprocessor interrupts. Okay, but it's beyond the scope of 124. Probably, thankfully, it's beyond the scope of CS124. Okay, what's the upshot? Well, I want to talk a little bit about this interrupt handling, because important things always happen when you get into the kernel via either a trap or a hardware interrupt. Very important things happen. So it's really valuable to spend some time understanding what happens when you get into the kernel, what happens on the way out of the kernel. And I know that we're going to be revisiting this multiple times because there's a lot of important details. Okay, hard disks. You access, now I know probably all of us don't have hard disks to access unless it's some external USB device you use for backups. If you read something off of a hard disk or even an SSD, you are burning anywhere from hundreds of thousands to millions of instructions, because the program is simply not able to proceed until that external peripheral access completes. So the upshot of this is when you perform these long-running operations, almost always the operating system will set it up and then perform a context switch to a different process. This is what this picture over here on the right is indicating. Program A issues a read through a system call, so you trap into the kernel. The kernel sets up the read operation, and then the kernel knows program A can no longer progress because it's now waiting for this read to complete. So what it does is it finds another process that's able to proceed, and it does a context switch to that other process. So in this picture, it's program B is now going to get to run. Now, at some point, the disk controller says, hey, your data showed up. Okay, so a lot of magic happened. And so what happened is you get a hardware interrupt, and it interrupts whatever program is currently running on the processor. And the kernel says, this is the disk controller. So it talks to the disk controller, finds out what data is now available, moves it into a kernel memory buffer, figures out what program was waiting on that data. Now that program is runnable, so it can context switch back to that program because it can now proceed. Okay, you can see that I always like to say that operating systems are basically incredibly sophisticated bookkeepers. They just have to keep track of a lot of stuff. The hard part of OS implementation is twofold. You're talking directly to hardware, and hardware sucks. And the other part of it is that things can interrupt other things like all the time. And so that's what makes writing operating systems complicated. If you don't have those things to worry about, they're not actually half bad. Okay, so this is just the summary slide of what we'd like to have on hand to implement a modern operating system. Last time we talked about dual mode execution, kernel mode and user mode. We talked about virtual memory management because this is how we build address space isolation between processes and kernel user space isolation. The ability to trap or somehow get into the kernel. Support for software interrupts, traps, and faults, as well as hardware interrupts, so that hardware can tell us when it's ready to do things for us, or it's finished doing something for us. And then also a hardware timer facility so that we can build preemption. If we have these things on a processor, we can build a pretty damn good operating system on that processor. If we don't have those things, our lives will be correspondingly reduced in quality. And I'll talk about an example of that really shortly. All right, yeah, so we'll talk a lot more about this as we get into those corresponding details. Are there any questions? Does anybody have any questions about this hardware OS interdependency? If anybody does, feel free to blurt it out or drop questions into the chat, because we are about to shift topics somewhat. Okay, I'm not hearing anything, so we shall go on. There are some common structural patterns that you see in operating system implementation, and it's a good idea to be aware of these. Ooh, good question. Is there a formal definition of a bus? There may be a formal definition of a bus, but what I can tell you is an informal definition. A bus is simply n wires, where n is the bit width of the bus, and it's used to route signals between different components within the processor. So, for example, like we talked about the APIC bus. And what I would say is there tends to be a little bit more detail than just it's a bunch of wires, because you have to also talk about how components use the bus to communicate. So, for example, the APIC bus will have control signals which say, who do you want to talk to? Like, what processor do you want to talk to? Each APIC has its own ID. So, and then you'll have, these are data lines, these are addressing lines, these are control lines. So a bus is much more than just a bunch of wires. It's also a protocol that you use for interacting with the bus. I think that'll probably have to do for now, but if you have more questions about that, feel free to bug me, because it's really interesting, actually. I'll just tell you this one thing. The PCI bus is very common in modern desktop computers, and it needs to support multiple bus masters, because a peripheral, like a disk controller, can dump data into memory directly without actually involving the CPU. So you have this notion of bus mastering. The bus protocol needs to be designed to support that. We'll talk about that a lot more in the future. Okay, so as far as OS structural patterns are concerned, there's one overriding consideration which is really valuable, which is called separation of policy and mechanism. Policy is what you want to do, and it's more of the why, right? There's a lot of more like sort of high-level theoretical considerations at that level. And then mechanism is how. And that's typically where the hardware-dependent bullcrap lives. So policy, what needs to be done? Which virtual memory page should the OS evict? What process should the OS run next? If you happen to have a mobile device, how do you decide what power level it should run at? How do you decide when to turn on the cellular radio and when to turn it off, and at what power level the radio should run at? All of that kind of stuff would be governed by policies. Mechanism is how you do it, how you talk to the hardware to do the thing that the policy says it's time to do, okay? And it should be obvious why we want to separate these things, because one of them basically never changes. Like, you know, I just got an iPhone 12, and as long as I have an iPhone 12, the hardware is fixed, so the mechanism is fixed, but the policy may change from OS update to OS update. So we want to decouple these things so that we can tinker with the policy or configure the policy, and the mechanism will basically be unchanged. Okay? So lots of things that you can do there. Another example, I don't know if any of you have Android phones, but Android has this thing called the governor, which controls how fast the processor runs and how much power it uses. And the governor is something you can configure as a policy in the OS. How it does its thing is mechanism. And so that lives outside of the governor. Okay, now besides that general principle, and there's all the other software engineering principles you'd like to follow like modularity and debuggability, and all these things do inform OS design. At least you hope they do. Otherwise, it's probably going to be a crummy OS. But operating systems do have a handful of patterns that they follow. The simplest one is called simple structure. It basically means no structure. Maybe some level of class level modularity or some kind of modularity, but you don't really have a clean division of modules within the OS. Every part can talk to every other part. That is kind of a recipe for chaos, it turns out. I know that comes as a great surprise to all of us. But this tends to happen when you don't think at all about how you want to design your OS up front. So you probably can imagine a great example of an OS that had this kind of structure is MS-DOS, because MS-DOS emerged in a very ad hoc, organic way because Microsoft had the opportunity to scoop CP/M, the CP/M operating system, for IBM, and so they did. They threw together an operating system very quickly. The rest is history. Thankfully, it's distant history by now. So problems are, as you would expect, susceptible to OS and application bugs, easy for malicious programs to exploit. And I know, because that was one of my favorite hobbies when I was a kid, was learning about computer viruses and how they work and how they compromise the operating system. Now, most of those mechanisms simply can't be implemented because the OS is too capable of preventing them through protection and isolation and all of these other things. So 8086, 8088 processors. Well, we had a hardware timer. We didn't have a virtual memory unit. We didn't have any kind of memory management unit. We didn't have protected mode versus user mode. So you can't build a decent operating system on an 8088 processor. It just isn't possible. And so we ended up with the chaos we ended up with, and it was just that way. So as I have on the picture, applications could talk to the hardware. In fact, they had to talk to the hardware because you did everything through BIOS. Or if you wanted to write a computer game that did fancy pants stuff with the graphics hardware, you talked directly to I/O ports. I did that kind of stuff all the time because it was super fun. You could terminate and stay resident, so you could actually modify the way that the operating system was working. You could register, you could override the interrupt handlers for the operating system, which is crazy that it even was allowed, and all kinds of other things. All right, and malicious programs made great use of this by intercepting operating system handlers and even BIOS handlers and obscuring the fact that they were present in the system. So malicious programs could basically do whatever they wanted to. It was pretty remarkable and exciting as a teenager. It was a lot of fun and motivating to get into all of those implementation details. In a sense, I'm kind of sad you don't get to have that experience yourselves, because what a world to live in. It was really quite exciting. Let's see. So UNIX initially was more structured than DOS simply because of the fact that you had the kernel and you had the stuff outside the kernel. So that imposed a bit more structure than just straight everything's in the same box kind of universe like MS-DOS worked within. But you did have that division, and the kernel itself internally wasn't really very structured either. And so this gave rise to this kernel architecture called monolithic kernels. You've probably heard this term. You probably still hear this term because it is accurate to describe Linux as a monolithic kernel. And well, I won't go on any more than that because we'll talk more about this on Monday when we introduce the other end of the spectrum and everything that lives in between. So we'll talk about that a lot more. Yeah, I see somebody mention Linus. A great flame war erupted between, I want to say Andy Tannenbaum, I think I got that name right, the creator of Minix, and Linus Torvalds, creator of Linux, of course, over this question of monolithic kernels versus microkernels. And you can read all about that if you want. I'll probably have a lot more to say about that on Monday. Okay, monolithic kernels are scary because everything can talk to everything inside the kernel. So you're not really protected from kernel bugs. Everything goes sideways if the kernel has a bug that manifests. Okay, so I talked a little bit about this. It's definitely problematic for a number of reasons, and so it's not really a recommended approach. There are variations on the monolithic kernel approach that people now take, and we'll talk a little bit about this. The reason why we still like it so much is that monolithic kernels are fast. When you don't have abstractions, anything can talk to anything, anything can access anything. It turns out that that's super fast. And so that's why people still really like this kind of approach. Okay, so Windows NT is a great example of this. Of course, Windows NT is sort of the predecessor of the modern Windows 10, Windows 8, Windows 7 operating systems. And NT was an attempt to go the other direction, modular microkernel architecture. It was too slow. So they started pulling stuff back into the kernel to make it more monolithic. I said I would wait till Monday, but I couldn't help it. Okay, so monolithic kernels are super fast, which is why people still do them this way. All right, another structure is the layered structure or layered architecture. And this can be employed in a lot of contexts besides just operating system implementation. But there was a specific experiment done with building a layered architecture operating system, where basically every layer exposes an API, and the layer above can only interact with the layer below through the API. You can't access any state directly. You can't jump layers. You have to only talk to the next layer, okay? And so the idea behind the layered architecture is that once you have a layer, you can write exhaustive tests for it, exercise that layer, and you can be sure that it works when you start building the next layer on top of it. Okay, so this was the idea behind the experiment. The OS is named the OS, which sounds really strange, but THE is actually the acronym for the university where it was developed, and I don't know what language that is. I will confess ignorance, but I do know that it is basically the Eindhoven University of Technology is the translation, but Technische Hogeschool Eindhoven is THE, and so it's the multiprogramming system. This also tells you that this is a much older batch processing operating system. Okay. Edsger Dijkstra was involved, which is kind of cool. Another brush with greatness here. And the OS basically had 6 layers of implementation. And each layer would only talk to the layer below it, although you might have higher level layers that interact with a few layers. Okay, I think it's called layer tunneling when you have that kind of an architecture. And so layer 0, of course, this is what computer scientists would do, right? The bottommost layer is layer 0. And you'd build that layer, exercise it, and then you'd build the layer above it, okay? So this was really great. There was a lot of careful design, a lot of careful test review, because this was a batch processing system. So you get your stack of punch cards, you drop them into the hopper for the computer operator, walk away, have a nice lunch or whatever, come back later that day, get your output, and see whether or not the test passed. So it forces you to think carefully about how everything is designed before you try running it, okay? So let's see, layer 0 is multiprogramming. So multiprogramming, remember, is the predecessor to multitasking. So program isolation, so process isolation, and how program memory is managed, all of that kind of thing, scheduling. Layer 1 is virtual memory and the virtual memory pager. Layer 2 is communications. Layer 3 is device I/O. And layer 4 is user programs, so compiling, running programs, printing output, that kind of stuff. And then layer 5 is the user, which I think is hilarious that layer 5 is part of the stack. But there you go. Now, the upshot of this experiment was this OS was pretty freaking awesome straight from the start. It had very few bugs. The bugs that they did have were easy to identify and fix. They found that the implementation process was very slow, as you would expect, because there was a lot of upfront design and a lot of upfront consideration, sort of Zen debugging, where you stare at the program before you take it over to the operator to run it. The whole write code, run code, test code, see the output was a lot, that process was a lot longer back then, so it forced you to think carefully. Now you just run it and see what happens. They found that this layering made the OS super slow because it was always bouncing down and up through these different layers. Okay, so of course, one of the things that they realized is, well, maybe we could have had fewer layers, although you're already at 6 layers or 5 layers if you count software. There's not a lot fewer layers to have in a system like that. So what can you do? Hopefully you're starting to see why monolithic is still kind of the approach du jour these days, because speed is really important for people to be happy with their computers. Okay, the last one that I want to talk about today is starting to venture into a slightly different architectural approach, but we won't really broach that topic until Monday. Modular kernels are basically a solution to a problem that emerged relatively quickly with monolithic kernels, which is you're putting everything in the kitchen sink in the kernel, and you almost have to. Think about Linux. Now, when I was an undergrad, when I was your age, and I remember my first internships at Microsoft, and I'd go up to Microsoft with my desktop computer, and I'd get my apartment with another Microsoft intern, and the intern would say, "Hey, I got the latest Linux distro. Do you want it?" And I'd say, yes, I'd love that, because the internet wasn't really widespread at the time. Wi-Fi didn't exist. And so what I would get from my buddy is a stack of like 20 3.5-inch disks, and you just feed them into the computer to install your OS. Well, why was that? Linux was trying to support a whole bunch of different hardware configurations. How do you support a bunch of hardware configurations? By having every possible hardware driver that you care about packaged into the kernel, right? So you had no escape. I have to support every kind of sound card in the kernel if I want to make sure that I have a good chance of supporting user X's sound card. Same thing with graphics cards, same things with wired network cards, all of these things. So if I want to support a new device, well, I have to go into the kernel config, and I remember doing this. I did this a lot when I was younger. Go into the kernel config, turn on and off support for various devices, recompile the kernel, reinstall the kernel, start up the computer, hope that it works, because you're changing the kernel, right? I mean, this is a big deal. So you can see how this would create major problems. The kernel becomes big because you're trying to package everything into it. And because you're packaging everything into it, you have more potential, bad interactions between pieces of code written by different authors and so forth, more chance for bugs, more chance for instability. And certainly you have an increased slowness because your kernel is huge. And one of the rites of passage when you would run Linux back then is you would try to get to the point of competence where you could configure the kernel yourself, and you try to streamline it as much as possible. You had to, because everything was compiled into it. Now we don't do that because of modularity, and it's really neat. So basically now the kernel includes a dynamic linker, so that you can load kernel modules off of, what is it, like insmod, lsmod, and I'm trying to remember, modprobe. I don't remember. I don't do these. I'm on a Mac now, but those are the kinds of things. If you're on Linux, poke around. You can see kernel modules that are loadable and linkable into the kernel. Okay, and so we call these modular kernels. Now, there's certain things that are always compiled in. makes sense, right? There's certain things that are required to be an OS that doesn't suck. So virtual memory management, paging, process address space isolation, your process scheduler. A lot of those things are always compiled in. Support for things like FAT and support for things like your standard file systems, maybe BetterFS, maybe ext4. It depends on what you're configuring the system for. Okay, so the kernel has interfaces for the parts of the kernel that you'd like to be able to extend, probably file systems, graphics drivers, block devices, things like that. And then it includes this dynamic linker that basically allows you to load a module, statically link it into the kernel so that now the module is loaded into the kernel. Now, what you'll notice about this is that the module still lives in the same bucket with everything else. So do we really have that much of a deviation from a monolithic kernel? Everything can still access everything else. It's just that we have a much more streamlined and customizable module loading mechanism built into our kernel. That's all we've really changed. And that's kind of important. So the benefit, you retain the high performance of a monolithic kernel because guess what? You still have a monolithic kernel. Modules can, to some level, control the symbols that they expose. Okay, so that's nice. You can just not include name bindings for certain symbols that you don't want to expose. But another kernel module could still scan your kernel module's state and code and figure things out. So this is why you have to be real careful about what kernel modules you include. And you get a much smaller kernel footprint because you only load the stuff that you need. Okay? But the issue is that it's still monolithic. It still has everything in kernel mode, and it's all still in the same bucket. And so you can still end up with reliability and stability issues over time. Okay? So the thing to keep in mind is what I say here. A modular kernel doesn't necessarily have a more well-defined structure. It's just easier to extend the kernel with a loadable kernel module. Okay, let me see. We're almost done here. So I already talked about this. Stuff that you always need, or you're pretty sure you'll always need, usually gets compiled in always, because why not just include it in the kernel, okay? Yeah, and this is kind of the key takeaway about modularity and monolithic kernels. The term monolithic kernel refers primarily to how much OS code runs in kernel mode versus in user mode, okay? But modularity you can think of as being sort of an orthogonal dimension. Like you have a monolithic kernel, but it implements a kernel module system that makes it a lot easier to extend or customize without having to rebuild the kernel. I imagine probably none of you have had to build your kernel from scratch on Linux unless you just totally want to. Now it's just not necessary to do so. Okay, any questions about that? Quick questions. If you have slow questions, I'll hang out on the Zoom so that you can ask any questions. What we will do next time is talk about the other end of the spectrum, which, like I've given away, is microkernels, and they're very cool technique, and it's actually becoming increasingly common. So that's it for now. I will see you on Monday.